And welcome to the last lesson of this unit on rational functions, rate of change. It feels like we've done rate of change every unit, and that feels like that we've done rate of change every unit because we have done rate of change every unit, and we know that the unit is just about done because we're doing rate of change yet again, revisiting an important topic from this course and how it fits in with rational functions. 3-minute review is to graph this, and boy, oh boy, have we done a few graphs of rational functions, but we're getting pretty good at this. X and Y intercepts. When X is 0, Y is negative 1/3, right? Just put in X is 0. Then we find the X intercepts by setting that equal to 0, cross multiply, and we see X is negative 1/2. Vertical asymptote is when the bottom is 0, right? And we could cross multiply as long as it wasn't equal to the vertical asymptote of x equals positive 3. The horizontal asymptote is top and bottom have the same degree, so it's the quotient, the division of the leading coefficients, which is 2. And now we're off to the races here. X equals 3. Quick. Want to get through this. Want to start my review. There's y equals 2. And I get my 2 points. X is negative 1/2, 0. Negative 1/2. X is negative 1/3. Or X is 0, Y is negative 1/3, right in there. And now, I'm not even going to need to check behavior near that vertical asymptote because it's got to go through these 2 points. It's got to get close to the horizontal asymptote. It's going to work like this, isn't it? Over here, I suppose, I don't know. Maybe I should try a point, put a point in there, just to get like a scale about how slanty this is. Trying 5. So I get 2 times 5 plus 1 over 5 minus 2, 11. 5 minus 3 is 2, 5.5. 5.5 right there. I would have went pretty close to that anyway. It kind of looks goofy, but that's all right. Good. And that would give you full marks there, folks. Perhaps I should put labels on the axes and arrows on my graph, but that's the work that we need to show to do that graph. Now, probably, I'm guessing we're going to want to try and find some rates of change. Remember, rates of change are connected to things like secants and tangents. So we'll calculate the average rate of change over that interval. Remember, rate of change is just the slope, right? Average rate of change is y2 minus y1 over x2 minus x1, right? And here, my x2 is 2, my x1 is negative 1, and I can calculate my f values. F at 2 is, fire that into a calculator, 2 times 2 plus 1 over 2 minus 3, which is negative 5. F at minus 1, bing that into a calculator, bing. Negative 1 minus 3 is a fraction of some sort, unfortunately, a quarter. Negative 1 over negative 4 is positive a quarter. So I have negative 5 subtract a quarter over x2 is 2. Subtract, watch your integers here. And then I get, pop that into a calculator again. It looks like around negative 1.75. Notice average rate of change goes with the secant, and that's what we're going to come up with in part C, a secant here. But average rate of change that's negative means the graph is decreasing. And indeed, from negative 1 to 2, yeah, the graph is decreasing. And we're going to put that secant on there in part C. notice I'm going to change colors here. For B, estimate the instantaneous rate of change for X equals 100. Well, remember we had the ROC, and the estimate is, we know one of these values has to be 100, and the other one is one that's really close, either really close on the left or really close on the right. And in fact, last unit we came up with a different little formula for this, talking about, since we don't really care about x2 and x1, we really only care about the 100, that we can just choose how far apart the 2 points are, right? A is 100, and I pick H to be as small as I possibly have patience for, and my favorite is 0.01. That's what I always use, but that's up to you. And now notice that here, if I have this as 100.01, and I get some awful expression that looks like this. And this is pretty hard because these are going to have a lot of decimals, right? You know, I have a rational equation with all these decimals. I might want to try to put that into my calculator in one step. And I'll show you what I mean. So f at 100.01 is going to be 2 times 100.01 plus 1 all over 100.01 minus 3. That's f at that. Subtract f at 100. And this way, the calculator is going to deal with all the decimals as, you know, with that degree of accuracy that it possibly can. Let's I'm going to get my graphing calculator revved up here, and to show you what that might look like on a graphing calculator, so you can see where to put brackets and stuff. I'm going to have to pause the video to get that started. Okay, bam, there's the graphing calculator. And it's not that you can't do this calculation on your scientific calculator. And in fact, that's why I'm choosing this one, because it's a lot like your scientific calculator. Because a lot of your calculators, you can see what you're typing, and that's what I like. So big bracket, and then notice inside I have a rational expression as well. So I need another bracket right here in order for the calculator to know when this big division bar is. So this bracket sort of goes with this top thing, and then I'm going to go bracket 2 times 100.01 plus 1 bracket, and that's this bracket, divided by, and I suppose I could do some of this in my head. I know what 100.01 subtract 3 is, but oh well. 0.1 subtract 3, and that's this end bracket, and then I've got this big bracket, subtract big bracket, little bracket, top, 2 times 100. The graphing calculator doesn't like. There we go. 2 times 100 plus 1. End bracket there, that's this bracket, divided by, I'm not putting 100 subtract 3 in my calculator. I'm going to just do that in my head. End bracket. So that is this end bracket. Now I'm going to press equals. I'm going to press equals so that I get this is this top part. Now I got to divide by 0.01, and I certainly could have put that into my calculator again, but I would have had to put big brackets on this, and I would have had a whole bunch of brackets. So instead I pressed equals, I get that answer, and then now I'm going to divide that answer by 0.01, and I get my answer. And that's pretty nasty looking. I'm going to, you know, what does this E minus 4 mean? Well, that means whatever this number is, this is scientific notation. I'll write that in scientific notation. 0.44 about times 10 to the exponent negative 4. That means to go to the left 4 spots. So this goes to the left 4 spots. 1, 2, 3, 4. Negative decimal 0.0007 44. So what does that mean? That means it's still decreasing, right? Negative still means it's decreasing. Decreasing, but very small. But very slowly, right? Since it's so small. And that makes sense. If I were to go to the graph, way out here, now I obviously 100 would be way out to the right, but I can see it's decreasing quickly in here, but then very slowly. Think of even at this would be maybe x equals 10. The tangent's very slow. If I were to keep going, could I convince you that it would have a slope of negative 0.00074? Yes. The graph is approaching. The graph is approaching the horizontal asymptote. And in fact, this calculation also tells me, because it's going downhill, it's approaching the horizontal asymptote from above. If it were approaching from below, it would be a positive small number, right? Because it would be going uphill. So that calculation gives me a little bit of hint about what's going on in the graph. All right, so that's B. And nasty, nasty calculation. We realize that. Include the secant and tangent on your sketch. All right, so the secant, remember, is ROC. I'm going to put that on there. This is the secant. And this is going to be the tangent. Right? ROC, instantaneous rate of change, tangent. Secant is the average rate of change. All right, so let's put that back on our graph. From negative 1 to 2, right there. Could I convince you that, whoops, that slope is negative 1.75? I bet you I probably could. Let me see if I can do that. That's not bad. I know I can adjust, but you just use your ruler, right? Arrows on both ends. And then I'm going to write on here the slope of the secant was negative 0.75, certainly decreasing from this interval, negative 1 to 2, decreasing by 1.75 units. Now, what about the tangent? The tangent, obviously I can't go way out to 100, but I'm gonna pretend. I'm gonna pretend I can, and it's going to be a tangent that's really, really, really slow and negative, right? Really, really slow, and almost zero. It's almost horizontal. It's almost zero, but it's not quite. So, and I know this is a bit silly. X equals 100 out here. Would be the tangent at x equals 100, and I'm going to write down that it's negative 0.00074. That's the slope of the tangent there, the estimate of the ROC. And I'm going to point out something in part 2, which I have to be very aware of, and I'll get to that in part 2.